this lecture, I'm going to talk about how to do acid-base equilibrium calculations. So first off, why do we want to do this? Well, it'll become really important if you want to know the pH of a weak acid. But before I do that, I want to review the difference between a strong and a weak acid, and also talk about how to find the pH of a strong acid solution. So let's think about our two acids here. We have hydrochloric acid, which is strong, and hydrofluoric acid, which is a weak acid. Both of these can interact with water and produce hydronium ions. With HCl, since it fully dissociates, all of the HCl becomes hydronium and chloride. However, with hydrofluoric acid, since it is a weak acid, it does not fully dissociate. And so, while you will have some hydronium ion and some fluoride ions, at equilibrium, you will also have HF, whereas the strong acid fully dissociates. So let's say we start off with some HCl that has a concentration of 0.1 molar. Well, that means that the concentration of H3O plus is also 0.1 molar. And since the pH is the negative log of that concentration, it's the negative log of 0.1, which means that our pH is 1. So what if we start off with HF and we also have 0.1 molar? Well, we don't necessarily know what the concentration of this is at equilibrium because this has not fully dissociated. So how are we going to do that? If you guessed ice table, you are correct. So we are going to apply the principles of equilibrium problems that we used in our last chapter to acid-base problems. Now again, this is only for weak acids. If it's a strong acid, the concentration of the original acid is the concentration of the hydronium ion, and it would be the negative log of that concentration, and that would be your pH. But for weak acids, you would have to use an ice table. And so this is set up for hydrofluoric acid, a weak acid, and so you would know the initial concentration, which I gave you was 0.1. And then although this H3O plus here technically is not 0 because water has some H3O plus, but it's 1 times 10 to the minus 7th molar, which is really small, right? Because this is 0.1, so it would be 0.0000001, so it's really insignificant. So what we would do is we'd say approximately 0, and then our fluoride ion would be 0. And then one of two things will happen when you solve these problems. You'll either know what your Ka is, and then you can solve for this, or if you know what your final pH is, because you know what the concentration of this is at the end, you could calculate your K value. So let's do an example. In this example, we want to find the hydronium ion concentration in 0.1 molar HCN, hydrocyanic acid. So I have here our components and our ice table, and remember, we don't care about the liquid water because the change in concentration is negligible for that. So we're only going to be worrying about these pieces. So let's start by making sure we know what our K expression looks like. So our K value will have the hydronium ion and the cyanate ion on top, and then would have the hydrocyanic acid on the bottom, okay? And we have our ice table. So let's fill in the values that we know. So our initial concentration of HCN is 0.1 molar. So for our HCN, we can put in 0.100 here. And then we're going to do that almost nothing for H0 plus, because again, it's like 0.0000001, which is like way beyond the number of sig figs we have, so it's totally irrelevant. And then our anion would be 0. Okay. And so now we need to figure out what to put in the rest of our table. Well, we know that we're going to lose some amount of our acid minus X, and then we will gain some hydronium ion, and we will also gain some of our conjugate base. So notice how these are all single X values, because we have there's no coefficients in here, right? So it's just you lose one proton, gain one proton here, so it's all 1 to 1, so we just have our X's there. And then now we'll be ready to fill out the rest of our table. Now we don't know what X is yet, so we're just going to keep it with our variables. So 0.100 minus X, X, X. Now we can take all of our values here and put them into our equilibrium expression. So we can set our Ka value of 4.9 times 10 to the minus 10th equal to x squared over 0.100 minus x. So that x squared comes from the fact that we have an x and an x here, and we're just multiplying those together because that's what the values are from our ice table. And so how do we solve this? Well, one of the ways we can do this is by using the quadratic formula and doing a lot of algebra. So just be careful as you work through this. So I'm going to write everything out so that you can see how it all happens, and try to follow along and maybe sketch it out with me. So we take this denominator and we multiply both sides by this, distribute this, and then set the whole thing equal to 0. So I'm going to do that. So I multiply by 0.100 minus x. Those cancel. Okay. And then I distribute. So now I have 4.9 times 10 to the minus 9th minus 4.9 times 10 to the minus 10th x equals x squared. And then I will subtract this value, I will add this value to both sides and subtract this from both sides. So now I have this nice quadratic equation, x squared plus 4.9 times 10 to the minus 10th x minus 4.9 times 10 to the minus 9th equals 0. So now if I want to use the quadratic formula, I can actually solve for this. And what you'll want to remember is that when you're using the quadratic formula, you want to know what your actual the values are in the equation. So this would be, your a term would be a 1 because there's nothing in front of the x squared. This here is your b term, 4.9 times 10 to the minus 10th. And your c term is negative 4.9 times 10 to the minus 9th. So you can use the equation, the opposite of b plus or minus the square root of b squared minus 4ac over 2a. And you're going to get two answers to this because you have that plus or minus there. Now, one of these will always give you nonsense. It's either going to give you a negative concentration, which you can't have, or it'll be just a negative number overall. So don't worry about trying to figure out which one is which. It will be obvious to you. Now, I'm going to show you a little trick because notice how tiny these numbers are. And let's go ahead and just pretend that the loss of this amount right here is negligible. All right, so what would that look like? So I'm going to get rid of this stuff here. And I'm still going to keep my k, my equation set up that way. So I've got my 4.9 times 10 to the minus 10th equals x squared divided by 0.100 minus x. But I'm going to assume that that x is negligible, so I'm going to get rid of it. And I'm just going to solve this now. So now what I have is something really simple. I've got 4.9 times 10 to the minus 10th times 0.1 equals x squared. So I can write that as 4.9 times 10 to the minus 9th equals x squared. Take the square root of both sides, and my x value is now equal to 7 times 10 to the minus 6th. So you're probably thinking like, ooh, that looks amazingly easy. Can I always do that? Well, not necessarily. So you have to figure out if your assumption is valid. And the way that you do that is you look at the ratio of x and the number that it was subtracted from. And you want that ratio to be less than 0.05 or 5%. So, in other words, if x is less than 5% of the value that you were subtracting it from, so 0.1 in this case, it's valid. So how do I know that? Well, let me figure this out. So I take my 7 times 10 to the minus 6, divide by that 0.1, multiply by 100, and that is equal to 0.007%. So that's real small. And so our concentration of our H3O plus is 7 times 10 to the minus 6th. pH wasn't actually asked for. We only wanted the hydronium ion concentration, and we have solved it. In this example, we want to find the H3O plus concentration and pH of 0.2 molar nitrous acid, and we're going to use that X is small approximation. So in order to do this, you want to make sure you know what your equation looks like for the chemical reaction so that you can make sure you put the right species into your ice table, and also check that you have the right Ka value. So we're given that. So this one's pretty straightforward. So we'll start off by constructing our ice table. So we'll have our nitrous acid, our hydronium ion, and our nitrite anion. And then we'll have our initial change equilibrium. We know that our initial values for our nitrous acid are 0.2, and approximate hydronium is about 0, and the nitrite is actually 0. Okay. So now we can do our change of minus x plus x plus x, and then 0.2 minus x, x, and x. So now we can set up our Ka expression. So we'll have our hydronium ion and our conjugate base in our numerator, and our intact acid in our denominator. So we can set up our expression of 4.6 times 10 to the minus 4th equals x squared over 0.200 minus x. Now remember, we're going to use that x is small approximation, so we can ignore this guy right here. And so we just have to multiply both sides by 0.2 and take the square root. So our x value is going to equal 4.6 times 10 to the negative 4th times 0.2, and it is the square root of that. And so x equals 9.6 times 10 to the minus 3. And so if we want to make sure that it's a valid approximation, then we can take our 9.6 times 10 to the minus 3 and divide by 0.2 and multiply by 100, and we get 4.8%. So it's barely okay, but it's still okay. So we're going to go with it. So this is our x value. So that means that our hydronium ion value is 9.6 times 10 to the minus 3rd, and our pH is equal to the negative log of that value, which means that our pH is 2.02. So let's do one more problem where we can't make that x is small assumption. So we're going to look here at this HSO4 minus, which is bisulfate, and we have a 0.5 molar solution of this compound, and we want to know what is the pH. Well, the Ka of this guy is not, still pretty strong for a weak acid. Its Ka is 1.2 times 10 to the negative 2. So let's set up our ice table. So we've got our bisulfite here, bisulfate, and our hydronium ion, and our sulfate anion. And we can write our initial change equilibrium. And we have 0.5, approximately 0, and 0. And then we'll have our minus x plus x plus x, 0.5 minus x, x, and x. So then we can set up our equilibrium expression. 1.2 times 10 to the negative 2 equals x squared over 0.5 minus x. So we're not going to make this assumption, because if we did, we would find that we would not meet that 5% threshold. So let's do the actual calculation instead. So the first thing we need to do is rearrange this equation. So we multiply both sides by 0.5 minus x, and we get 6.0 times 10 to the negative 3 minus 1.2 times 10 to the minus 2x, and that's going to equal x squared. Okay, so then we simply add this to both sides, subtract this from both sides. So now we have x squared plus 1.2 times 10 to the minus 2x minus 6 times 10 to the minus 3rd equals 0. So now we can actually solve our quadratic equation. And so again, that's your, is it the opposite of b plus or minus b squared minus 4ac all over 2a. Sorry, I just totally forgot what it was. I'm pretty sure that's correct. Yes, okay, that is correct. Okay, so make sure that you know what your a, b, and c values are. So our a value is 1 because there's nothing with our x squared. Our b value is 1.2 times 10 to the minus 2, and our c value is negative 6.0 times 10 to the minus third. Now, if you want to use a quadratic solver, you can, but you can also just plug it in here. And if you do that, you'll get two values, and you'll find that one of them gives you an irrelevant value, so you can't use it. So you need to have the positive value, and you get x equals 0.072. And so that is the concentration of the hydronium ion. So now you can find the pH, the negative log of 0.072, and that's 1.14. So the last point that you'll have to consider when doing these types of calculations is whether or not an acid is a strong or a weak acid. Table 16.3 in the 4th edition gives you the list of strong acids, and there are only 6 of them that are relevant, and they're really, really easy to remember. So 3 of them are just HCl, HBr, and HI, so hydrochloric, hydrobromic, and hydroiodic acid. And then the others are nitric acid, the HNO3, sulfuric acid, which I'll come back to in a second, and then perchloric acid, which is HClO4, which you will run into with the perchlorate anion as bleach. So sulfuric acid is interesting because you notice that all of these, with the exception of sulfuric acid, only have one H. So those are called monoprotic. So sulfuric acid is diprotic, meaning it has 2 protons. And in our last example, we looked at the second proton. That's a weak acid. So sulfuric acid is only strong for that first H. Is a strong acid. HSO4 minus is a weak acid. It does not fully dissociate in water. And so when you're given these problems, generally if you're given a Ka, you know it's a weak acid. But these are really the only 6 strong acids that you'll see. And honestly, you'll hardly ever see these. But like hydrochloric acid, nitric acid, and sulfuric acid are extremely common. And so you should be aware of those so that you know which type of calculation you should be doing. Is it a strong acid, then the pH is simply the negative log of the concentration of the original acid. If it is a weak acid, then you'll need to use your ice tables.